Hello everyone. In this video I'll be talking with you about an RC transient natural response circuit. So there's different ways to do this, and you can actually use direct integration or anti-derivatives in order to come to your solution. But what I'll be using is a method that actually reveals the roots of the equation and gives you a general sense in the of what's going on in the S-plane itself. So to start with, we're going to have this circuit where we have VDC, and our VDC is going to be connected up to R and C prior to time 0. So time 0 is like there, it's at 0, and we're going to reach steady state first, and then we're going to flip the switch and see what it does after t sub 0, that being t and then this being Vc of t. Okay, so now with that being the case, we're going to say that VDC, so this is prior to t sub 0, VDC equals VR of t plus Vc of t. VDC also equals what? Since the current going through the resistor is the same as the current going through the capacitor, we're going to just say IC of t times R plus Vc of t. Well, what is IC of t? IC of t is C times dVc of t dt. So then we're going to substitute that back into our equation here where we're making an application of it. So RC dVc of t dt plus Vc of t. Now at the time where we switch from here over to here, VDC will become 0. So now our equation results in 0 equals RC dVc t dt plus Vc of t. Now what we have here at this point is called a first order differential equation. Okay, again, I'll write it up here again. 0 equals RC dVc of t dt plus Vc of t. Now in this particular equation here, this is if you read differential equation books, they're going to call this a homogeneous equation or homogeneous equation because you don't have your forcing function in here, you just have your output. So you're going to be looking at what you call, again, your natural response. With that being the case, it's the response that the circuit makes without it being excited by any outside source. That's why you would call it the natural response. So with that being the case, what we want to know next is, well, let's solve this differential equation. Well, what can I do, or what function can I have that I differentiated and pretty much, you know, it fits this form where you have the function itself, you differentiate it, and it still equals 0. Well, the thing that meets that criteria usually is the exponential function, e to some power of x, right? If we differentiate, say, just in general, d dx, e of x, what do we get? We get e of x, right? Now, if we have a constant there, and we say d dx times a e of x, now we have a e of x, and so forth and so on. So what we're going to do is we're going to put in, instead of e to the power of x, we're going to put in a e to the power of st, because the st is some unknown constant that we don't really know about right now, but we're going to figure it out eventually. And we're going to assume that that is the solution to this equation. So that is what you would call just your general solution. So it's basically really off of an assumption itself. So we're going to assume that a times e to the st is a solution to this equation, and our mission is to find out what is a and what is s. Okay, so excuse me, 0 equals r times c d dt a e to the st plus a e to the st. And now when we differentiate that, what do we get? Well, we have RC, a comes out in front, and then we're differentiating st with respect to t. And so now we have a s that results from that, and we have e to the st plus a e to the st. Now that we have that, next thing that we want to do is we want to factor out things. And so we have 0 equals a e to the st times rc, we're still going to have s there, plus 1. Now, in order for this to be true, where 0 equals a times e to the st times rcs plus 1, we're going to make this equal to 0. Because if we put 0 here for t, then now be equal to 1, and we don't want our constant to be 0. So the assumption is that we're going to have rcs plus 1 equal to 0. So if that is the case, rcs plus 1 equals 0, we have negative 1 equals rcs, and then we're solving for s. So that means negative 1 over rc equals s. So again, in our solution here, our general solution, now what we're going to do is put in negative 1 over rc. Excuse me. So we have a e to the negative t over rc, and that is our solution there. Now the very next and last thing to do is to figure out, well, what is a? What is a? Well, whatever, okay, for a capacitor, if we charge up a capacitor has what we call an initial voltage that's over that capacitor. We're going to call that initial voltage the voltage at time 0. So we call it Vc of t sub 0. Now, depending on what this voltage source is, right, that's what the capacitance is going to be, the initial voltage over that capacitance is going to be. Well, why? Because over a long period of time, this is eventually going to be an open. If that's an open, it simply means that since the resistance here is like you use the voltage divider formula conception to conceptualize the fact that since this is an open, that's going to be infinite resistance, and so the total voltage drop across it is going to be, say like you have your voltage source there, all your voltage drop is going to be across that capacitance because effectively it's going to be an open. Okay, so with that being the case, you know that Vc of t sub 0 is going to be equal to VDC, right? So we're going to use that in order to figure out, well, what is A? Okay, so at time sub 0, okay, so this is our solution, our almost, it's like it's not general, but it's not completely solved. This is going to be our intermediate solution. We're going to say that A times E negative T over R times C equals Vc of T. Now, Vc of t sub 0, as we just discussed, is going to be equal to VdC. Now, if we were to take t sub 0, which is equal to 0 in this case, we have a times e to the 0 equals Vc of t sub 0, which equals VdC. Well, e to the 0 power is what? That's 1, right? So now we have a times 1 equals VdC, and so, of course, a equals VdC. But instead of putting VdC there, we can just simply say Vc of t sub 0, in order to keep it as general as we would like for it to be. So a equals Vc of t sub 0, which in this case happens to be VdC. So now that we have all of that said and done, Vc of t is equal to Vc of t sub 0 e to the negative t over Rc. Now, what is all the significance of this s, and why did I use s? Well, because that's the root of the equation. Now, with that being the root of the equation, this will just be an extra note, and this will be more important as you proceed onward into more studying all of this. But we have what we call the S-plane. And in that S-plane, we have what we call the real axis and then the imaginary axis. We're only in first order circuits here, so anything that is of the first order nature generally pretty much restricts itself to the real axis. When it's second order, then you have conjugate pairs that are something like there and there, but that's a little bit of a later lesson or lecture that we'll get into later. For right now, what we're going to take a look at is, well, where is S in this plane? Well, remember, we said that S equals -1 over Rc. So that's a real number. So where is that? Well, apparently, if this point here is 0, then -1 over Rc is somewhere here, as -1 over Rc being a constant itself, somewhere over there. So, well, what does that mean? Well, as we go more and more and more towards 0, let's say -1 over Rc equals 0. Well, then what would that mean for our function here? Well, it just means that e to the 0, okay, because that would be -1 over Rc equals 0 times t, it would make it 0, and e to the 0 would be 1, and that would just be Vc of t sub 0. So, in other words, let's gain some intuition here. If the resistance was very, 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 very large, and since it's on the bottom, if it's very large, it means that it'll approach 0. And if it approaches 0, what it means is that you'll have a constant Vc of t sub 0. This is why this is important. The response in the time domain would be this, and this would be Vc of t sub 0. On the other hand, if R was moderate and C was just very, very, very large, then it would have still the same effect, and you would have Vc of t sub 0, okay, as being kind of like a pretty much a static state of the circuit, and it would just pretty much stay that way. Now, if I go the other way and I start getting -1 over Rc is starting to become, instead of closer to 0, it's starting to become bigger. What does that mean? Well, that means less resistance or less capacitance. Well, what does that mean? Well, it means that this exponential function here will become more effective. And with that being the case, now you have Vc of t sub 0 following an exponential decay. So that is what you would gain as intuition from the root of this function in the S-plane. So that'll prove to be a very important thing as time goes along. So with that being the case, this is our final answer here, and that will pretty much do it for this video on RC transient natural response. So hopefully this video was helpful for you. Thank you for watching and have a nice day.